Mm, Hello guys, so I will explain you the numerical on stress strain diagram. So we will see that how should we solve, how to solve numerical on stress strain diagram. Okay, so if this word comes in front of your eyes, stress strain diagram, first of all we should draw the stress and strain for the mild strain, as this numerical is relevant to the mild steel only. Okay, so I'm drawing the stress strain diagram of a mild steel, and this is the shape of the object, or we can say in the right word, specimen, that is being subjected to the load in UTM, right? So this is the original shape of the specimen, and after it gets fractured, the shape of the specimen will be like this. So it forms a cup and cone shape fracture, right? Okay, so it's a fracture one, fractured specimen. You see fractured specimen, right? Okay, fine. So now if we plot all the points, important points out here, so it can be attributed to a P, this is a E, this is upper L point, so YU, this is YL, this is UT, ultimate tensile strength, and this is the fracture point. Fracture point. Okay, now what else is there? So yeah, I hope that you all know about all these things, right? So we don't have to explain much about that. I will be explaining it in my other videos. Okay, so what is given in the numerical problem is that a 10 dia specimen has a 50 gauge length. So this part is known as the gauge length. Okay, gauge length. Its value is 50 Okay, fine. And it is saying the 10 dia. So it means that its dia was at the initial condition 10 dia, right? You can say 5. Okay. Now the maximum load is 70. Here it is saying, that the maximum load is 70 means what? The load which is acting out here is 70 kilo Newton, right? And as we go down, the value, the magnitude of the load is going to get decreased, and that has come to ultimately 60 kilo Newton. It means that at this point, the fracture will occur, and this region is known as the necking region. Necking region. That's it. Okay, fine. So here it is also saying that we have got 0.2% offset is 55 kilonewton. Okay, so this is the, suppose this is the 0.2% offset from the 0 point on the x-axis. Okay, and if we draw a line which is parallel to this one here, then the load which is corresponding to this at about the L point, or we can say beyond the elastic limit, that will be known as the load at this point will be known as the proof stress. Proof stress. So it is very sure that the value of the proof stress out here, the proof stress, the load at the proof stress is 55 kilo Newton. It's the load at proof stress point, right? Okay, fine. Now what? The dia after the fracture is 8 so it might have gone lean, right? So that the final dia out here at the fracture will be 8 mm. Phi is equal to 8 mm. Okay, and the gauge length at the fracture is 65 mm. It's very obvious that initially the length was 50 mm and now the length has increased because we have applied the loading in such a way that its length has increased, that is known as the tensile loading, right? And it is its final length is 65 mm. Okay, fine. So all these are the values which is given in the numericals, right? So what we have to find out is what is the percentage elongation, what is the reduction in area. I have explained you that this determine the activity, right? And then we have to find out the tensile strength UTS. Okay, the load at this is given as how much? 70 kilo Newton. Strength means what is the maximum stress that it can bear at this point, right? Yield strength, yield strength means the yield stress, right? Fracture strength means the stress at the point of fracture, right? If E is equal to 200 GPa, the elastic recoverable strain at the maximum load, the elastic recoverable strain, how much strain will be recovered at the maximum load if E is equal to 200 GPa, okay? And if the elongation at the maximum load is 20%, then what is the plastic strain at the maximum load? So we have to find out the first one, that how much elastic how much elastic recovery has taken place, and then we have to find out that how much plastic strain has taken place if the elongation at the maximum load, that this is 20%. Fine. Okay, done. So now we see in the next slide that we have been given the area, or sorry, d dia is what? It's 50 mm, right? Right. Pi by 4 into d square, right? And area of the fracture is this one, 8 mm, right? So pi by 4 into, so it was in 10 mm, so mm they have changed to meter. For that 10 upon 1000, so it will be whatever, it will be 0.010, right? So they have found out the original area, and then they have found out the area at the fracture means what? We can find out that what has been the diameter at the fracture point. The diameter at the fracture point is 8 mm. Why? Because there we have seen that material goes under necking region. So the dia out here, DO and DF will be less than DO, right? Okay. Original gauge length is 50 mm. That was simple. When the specimen was loaded in UTM, it was like this one. And the gauge length at the fracture means, if we have to measure the gauge length at the fracture means, what we have to do is that simply we have to find the length from here to here after 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 temporary joining of the joints. We measure the length of the gauge, right? So what we do simply, suppose this has gone into two parts, A and B, we will simply join them manually, right? they are combined manually and the length is measured, right? In that case, they have found it 65 mm. Fine. Now we have found the values. So first of all, the elongation. So LF final minus L naught by L naught into 100. LF means what? The final gauge length, right? And this is the initial gauge length, right? So we have got the 30%. Reduction of area, right? This is A naught and AF. We know that AF will be less than A naught because at the fracture the dia at the fracture is what? 8 mm, and the initial dia has been 10 mm, right? So from here they have found out the decrease in the area. Now we have to find out the UTS, means the maximum load that it can bear upon the original cross-sectional area. The maximum load bear upon original cross-sectional area. Mind one thing out here, that we are finding the engineering stress strain value, but not the true value. No, because in true value it would be maximum load to the area at that instant. This will be true stress. But we always find the value for the engineering stress strain curve rather than the true stress strain curve. Okay, done. Now next, I have to get my slide clear now. Okay, fine. So now we see that yield strength. I've told you that we have to find out the yield stress, means the stress that would be induced in it when the load at yield point upon the original cross-sectional area. So in the numerical, it's there that the load at the yield point is 55 kilonewton. So that would be into 10 to the power 3 upon 7.54, as they found out, it will be 700 MPa, right? Fracture strength, obvious, the load at the fracture upon original cross-sectional area, right? Now elastic recoverable strain at the maximum load. It means what? See, elastic recoverable strain. Here we apply the Hooke's law. Where stress upon strain is equal to E, right? E value we have given in the numerical, right? And stress is what it is saying at the maximum load. So here we will be applying the P max upon A naught, and the P max upon A naught we have found out here only, right? So here it will be at 91 upon E. It will with the strain at the maximum. Fine. Okay. Thank you.